So welcome back, and today we'll see the last portion of the sixth module in your course, where the syllabus it is specified uh, why there is a need for an instrumentation system and a data acquisition system. So today we'll see why such a need is there and what is an instrumentation amplifier. We have seen what is an instrumentation amplifier in analog electronics course, but we'll see the application of instrumentation amplifier in this video. See, all through the module 6 we were seeing different types of transducers, different classes of transducers. So we have seen all those things. Now we have seen that almost all transducers barring a few gave an output voltage in millivolts. Only a few transducers gave output in volt, and we don't know how much current a transducer can give out so that it can drive an indicating instrument. That is another thing. See, many times it is seen that one point is the output is in millivolt. Another thing is that it may not have the capacity, or it cannot drive an indicating instrument like any analog instruments or digital instruments, or even if it can be a ZRO or a plotter, it cannot do that. It cannot directly drive such a load, such an indicating instrument. So in such cases, what is the solution? You cannot directly connect the output of a transducer to an indicating instrument. That is the thing, because it cannot drive such an indicating instrument directly. So what is the solution? So something should be in between a transducer and the indicating instrument, and that is what is the instrumentation amplifier, and that is a prime application of an instrumentation amplifier. That is why it is called an instrumentation amplifier. That is, it gives an amplified output to an instrument. So here we can see that, see, in thermocouple we have seen that the volt is in millivolt, the output is in millivolt. Only in the case of thermistors that we had an output in volt. So here you can see that the first stage, this is the block diagram, the first stage is nothing but a transducer plus a preamplifier. Some of the transducer, if you pay more, it will come along with a preamplifier. So the physical quantity to be measured, any physical quantity to be measured will be given to the transducer, and that will convert that into an electrical quantity, that is a voltage. So that voltage is given to an instrumentation amplifier, that is the intermediate step, intermediate block, and the output of the instrumentation amplifier, which is an amplified signal, is given to the output stage where we have an indicator or a process controller. So and we have seen that in between, that is, we are having transmission lines. So what is the purpose of transmission lines? See, the physical quantity to be measured will be inside a plant, and the indicating instrument and the instrumentation amplifier will be in some other location, in some remote location, or in some data center, or in some inside the room of a control manager or a controller or an operating person. So these physical quantity to be measured will be inside a hazardous region, or inside a very very adverse conditions. So you cannot keep an instrumentation amplifier or an indicating device inside such a hazardous environment. So it is always advisable to keep the electronic devices or systems inside a separate place, a remote place. So that is why transmission lines are used. So this is a block diagram of where how the physical quantity to measure is actually transformed into voltage, into a strengthened voltage and an indicating device. Then we'll see the next one, that is, suppose we take a resistive transducer. We have seen so many resistive transducers. So strain gauges we have seen, thermistors we have seen, then another one is photo conducting device, or a photo cell, or a resistive light dependent LDR, light dependent resistors. These are all cases of resistive transducers. We'll take an instance of resistive transducer and we'll see the circuit diagram. So basically, in an instrumentation amplifier we use a bridge circuit with an instrumentation amplifier, or we always take whenever it's a resistive transducer, we always follow a bridge circuit, because the one of the arms of the bridge will be that transducer. So what happens is that when the resistance of that arm changes, the balance configuration changes, and that will reflect into some output electrical voltage, and that is how we convert the corresponding changes in resistance to voltage. So we'll see such a diagram. We'll come back to this equation. So This is the circuit which I am talking about. This is the bridge circuit, a Beeston's bridge like circuit, Beeston's bridge circuit. Here the excitation is a DC voltage. You can have an AC voltage also, no problem. So this is the resistive transducer. So under the balance condition, this will have a resistance RT. So what is the balance condition? So that balance condition is actually fixed by a designer. For example, if it is a temperature transducer, you may keep the ambient temperature as a reference. Probably 25 degrees Celsius may be a reference temperature. So at that temperature, this will be the resistance. So at this resistance, the bridge is considered as balanced. That is, VB will be equal to VA. So under balance condition, VB equal to VA, that means that what is VB? VB is nothing but RB into RB divided by RC plus RB into VDC. So VB is RB divided by RB plus RC into VDC. Likewise, what is VA? VA is nothing but RA divided by RA plus RT. It's a balance condition, no delta R, RA plus RT multiplied by VDC. That is, VA is RA divided by RA plus RT multiplied by VDC. And that is what is shown here. So VB equal to VA. So this is the condition which I have explained. That is RB into VDC by RB plus RC equal to RA into VDC by RA plus RT. So this is the block diagram. And what is this? This is a well-known circuit called voltage follower. So VA is given to a voltage follower. So voltage follower, we know input is equal to output. So here also we'll have VA. Here another a voltage follower. So VB is the input. So this point we have VB itself. And the use of voltage follower is well known. It is used for impedance matching. And this is another circuit, another well-known circuit we have learned in the AEC course. And this is nothing but the differential amplifier. So the difference in VA and VB, that is VAB, is amplified using a differential amplifier, and that amplified voltage is given to an indicating instrument, or that is indicated by an indicating instrument. So this is the indicating instrument. So that voltage is actually given to an indicating instrument. So now what happens when we have, so when the balanced equation, so this was the balanced equation. So when I cancel VDC and VDC and and cross multiply, what you see is this thing, that is RC by RB equal to RT by RA. Usually we make RC equal to RB equal to RA equal to RT equal to R. So all these are normally made equal to a common resistance R. So this happens only under the reference condition. And what happens when VA not equal to VB? That is when RT changes. So that's the next condition we are going to see. That is when there is a change in voltage or change in resistance, that is RT gets increased or decreased by an amount delta R. So we'll see the mathematics of that. That is, VA now becomes RA divided by RA plus RT plus delta R, because earlier it was only RT, now it is delta, it is added by delta R. And VB more or less remained the same. VB is a constant. Why VB is a constant? VB is a constant because as we can see that RB and RC are fixed resistances. So RB or RC are fixed and VDC is also fixed. So VB is a constant. So VB is a constant, and so the only thing which is varying with the resistance is VA. So we can tell that corresponding changes in resistance is only reflected in VA. So what is VAB? VA minus VAB, VB. Substituting the values, we'll get this one. If I make RA, RB and RC, RT equal to R, I'll get this one. So we can see that this is a constant, R is a constant. So, and one more thing, this 2R is sufficiently a greater value than delta R. So delta R is negligibly small. So we can neglect that delta R, and we can approximate the output voltage, approximate VAB as delta R VDC multiplied divided by 4R. And we know the output. So this VAB is given to a differential amplifier. So we know what is a differential amplifier. Differential amplifier will have a gain of minus RF by R1. Here you can see that there is a minus sign here. It's actually not obvious here. minus sign shows that VB is greater than VA. So if I substitute this minus delta R VDC by 4R here, you'll get this equation. Here the approximation is not made here, so delta R is here. So we substitute, the minus and minus gets cancelled, and again this approximation is made, that is delta R is less than negligibly small when compared to 2R, so that becomes 4R. So this becomes VO, output voltage, is equal to RF by R1 multiplied by delta R by 4R multiplied by VDC. So this is an important equation, or this is the output voltage which we are feeding to an indicating instrument. So here you can see RF, R1, 4R and VDC are constant. So V naught, the output voltage, is directly proportional to delta R. So this is the case, that is delta R will reflect a voltage in the bridge, and that voltage is not directly given to the indicating instrument. Rather, we have an instrumentation amplifier stage in between, so that strengthens the voltage and give an output voltage V naught to the indicating instrument. And let me take an example. So this is a case of a temperature transducer where we have these conditions. Under balance condition, we have RA, RB and RC equal to 100 ohms, and VDC is taken as 5 volt, R1 is taken as 1 kilo ohm, RF is also taken as 4.7. You just refer the figure just I have shown now, and the supply voltages of op amps are plus or minus 15, and the transducer used is a thermistor, and RT equal to 100 kilo ohm at reference temperature. So reference temperature is fixed as 25 degrees Celsius. So this is my ambient temperature where I have my bridge as a balance condition, bridge at the balance condition. So the temperature coefficient of resistance, as we know that it is thermistors are having negative temperature coefficient, that is per 1 degree Celsius temperature difference, this is the change in resistance. Okay, and I have to determine the output voltages at 0 degree Celsius and 100 degrees Celsius. So by keeping this 25 degrees Celsius as my reference temperature, I'm assuming that I make the bridge balance. So what is the meaning of bridge balance? For 25 degrees Celsius, the bridge output voltage is equal to 0. So for 25 degrees Celsius, output of the bridge is equal to 0, and we have to find what is the output voltage at 0 degrees Celsius and 100 degrees Celsius. So what we have to first find, what is change in resistance. So from this one, this delta C indicates what change in temperature. So what is for 25 degrees Celsius, what is my change in temperature? So the reference condition is 0 degrees Celsius. My change in temperature is 0 minus 25 degrees Celsius. That should be multiplied with this one to get my delta R. So my delta R is 25 degrees Celsius. So when my temperature increases to 25 degrees, that is, this is my temperature now. This was my reference temperature. So the difference in temperature is 25 degrees Celsius and minus 25 degrees Celsius. And if that is the change in temperature, this much is the change in resistance. And if I substitute that change in resistance in the basic equation, what is the basic equation? This was my basic equation. That is, if I substitute that delta R here, RF is given, R1 is given, R is given, VDC is also given. If I substitute the delta R corresponding to 0 degrees Celsius, what I get is 1.47 volt. Now similarly, what is the voltage at 100 degrees Celsius? So for that we have to find what is delta R. So here earlier it was 0 degrees Celsius for which what we have calculated. Now we have for 100 degrees Celsius. So for 100 degrees Celsius, this is my temperature, change in temperature, that is 75 degrees Celsius is my temperature, change in temperature. So my change in resistance is minus 75 kilo ohms. So if I substitute minus 75 kilo ohms in my earlier equation, I'll get V naught as minus 4.41 volt. So for 25 degrees Celsius, it is 0 volt. For 0 degree Celsius, it is 1.47. And for 100 degrees Celsius, it is minus 4.41 volt. So the inference is that you can correspondingly make an indicating instrument which indicates that whenever there is 25 degrees Celsius, the voltmeter will show 0 volt, and whenever the temperature is 0 degrees Celsius, whenever the voltage is for 1.47, it is 0 degrees Celsius, and whenever it is minus 4.41 volt, it is 100 degrees Celsius. So you can indicate the instrument like that, just to show. Thank you.